chair beneath you, motionless. The floor under your feet, stationary. The walls around you, fixed. Every ordinary sense you possess confirms it. You are at rest, and the world around you holds its position while time flows forward. You are not sitting still. You have never sat still. And by the end of the next breath, you will occupy a position in space-time you can never return to. This is not about the Earth spinning, or the Sun orbiting the galaxy, or any of those familiar cosmological motions. This is about something far stranger, the possibility that motion itself, the very act of an object changing position across time, does not exist in the way you think it does. In 1908, a mathematician stood before an assembly in Cologne, Germany, and delivered a lecture that would rewrite the architecture of reality. His name was Hermann Minkowski. He had been Albert Einstein's teacher, and Einstein had published special relativity 3 years earlier. But Einstein's theory, in Minkowski's hands, revealed something Einstein himself had not fully grasped. Space and time were not separate stages on which events unfolded. They were two aspects of a single, unified structure, space-time, and everything you call motion was actually the static shape of that structure, frozen from a perspective outside it. Minkowski's exact words, translated from the German: "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He died 4 months later, at 44, of a ruptured appendix, never seeing the full implications of what he had begun. Here is what those implications are. Under the view Minkowski's geometry makes possible, a view now called four-dimensionalism, or perdurantism, or the block universe, every object you see is not a thing that moves through time. It is a four-dimensional shape, extended through time exactly as it is extended through space. The you sitting in your chair is a single cross-section of a much longer structure, a world tube that stretches from your birth to your death, every moment you have ever occupied and ever will occupy, already present as fixed geometry. When your hand slides across a table, it does not move. The hand is a static diagonal ribbon in space-time, a shape that happens to be sloped. Motion is not the act of crossing, it is the slope itself. Every position the hand occupies exists simultaneously, from a vantage point that sees all of time at once. There is no now sliding along that shape. The shape simply is, complete and unchanging, a fossil of every instant. And if that is true, then nothing you have ever witnessed, no car driving past, no clock ticking forward, no river flowing, no life unfolding, has ever actually moved. This is not fringe speculation. The mathematics behind it is the mathematics of special and general relativity, tested to extraordinary precision and woven into every GPS satellite, every particle accelerator, every prediction of space-time curvature around massive objects. The equations do not lie. What they describe is a four-dimensional geometry in which past, present, and future are equally real, and the passage of time is a feature of consciousness, not of the cosmos. In October 1971, two physicists named Joseph Hafele and Richard Keating boarded commercial airline flights with 4 atomic clocks. They flew eastward around the world, then westward, and when they returned, the clocks disagreed with the ground clocks by measurable amounts, minus 59 nanoseconds eastward, plus 273 nanoseconds westward. The numbers matched the predictions of relativity to within the margin of error. Time itself had bent. And if time bends, if it dilates and contracts depending on velocity and gravity, then it cannot be a universal river carrying all events forward at the same rate. It is a dimension, like space, and the flow you feel is an artifact of how your particular cross-section of space-time registers its neighbors. A hand sliding across a table, a planet orbiting a star, a photon crossing the void. Under four-dimensionalism, these are not processes, they are shapes. And once you see the shape clearly, the illusion of motion collapses. This is what you are about to understand, not as metaphor, as geometry. Step in. Press your hand flat against the table in front of you. Feel the solidity of it. The wood, or the glass, or the metal, whatever material it is, resists your touch. Your hand is here, at this location, at this moment. That is the intuitive picture, a single hand, wholly present, occupying one position in space while time flows past it. Now slide your hand 6 inches to the right. You have just moved it. That is what you believe happened. The hand changed its location. It was there, and now it is here. One object, 2 positions, separated by the passage of a few seconds. Minkowski's geometry says otherwise. In the four-dimensional spacetime he formalized, your hand does not move from one place to another. It is extended through both positions simultaneously. Picture a loaf of bread. Each slice is a cross-section, a snapshot of the loaf at a particular height. Your hand, in spacetime, is the loaf. The position of your hand at this moment is one slice. The position a second later is another slice. The motion you felt, the sliding, is not an object traveling. It is the shape of the loaf itself, a diagonal tube angled through the time dimension, connecting the starting slice to the ending slice. Every point along that tube exists, not existed or will exist, exists in the completed four-dimensional structure. There is no privileged now marking which slice is real and which is not. All the slices are real, coexisting as parts of a single geometric whole. The hand at the start and the hand at the end are both present, in the same way that the front of a ruler and the back of a ruler are both present when you lay it on a table. This is what philosophers call a world tube. For a point particle, it is a world line, a one-dimensional thread tracing the object's path through space-time. For an extended body like a hand, it is a tube, a four-dimensional volume whose cross-sections are the three-dimensional configurations the hand occupies at successive moments. The cross-sections are called temporal parts. Your hand, at 10:43 this morning, is one temporal part of the larger hand world tube. Your hand at 10:44 is another. Each temporal part is a thin slice, existing at a specific time coordinate, possessing the properties the hand has at that moment, its position, its temperature, the tension in its muscles, the precise arrangement of its atoms. The world tube as a whole is the hand, extended across time. And if that is the ontology, if objects are world tubes composed of temporal parts, then motion is not a process of change. It is a geometric property, the slope of the world tube, the angle it makes through the time dimension. An object at rest in space is a vertical world tube, parallel to the time axis. An object moving is a tilted world tube, angled through both space and time. The faster it moves, the greater the angle. But in both cases, the world tube is static. Nothing flows along it. The structure simply is, frozen in the four-dimensional block, and what you call motion is the pattern of how the slices are arranged. This is the ATAT theory of motion, articulated most clearly by Bertrand Russell in the early 20th century. An object is in motion if and only if it is at different places at different times. There is no additional ingredient, no dynamical moving through, no ontological passage from one location to the next. Motion reduces to a mathematical function, position as a coordinate along the world line, indexed by a time parameter. The velocity is the derivative of that function. The acceleration is the second derivative. Every quantity physics uses to describe motion is a feature of the static geometry, not evidence of genuine change. Consider a film strip. Each frame is a still image. When you project the strip through a projector at 24 frames per second, you see motion on the screen. But the motion is not in the strip itself. The strip is static. The frames are already there, fixed in sequence. The motion is an artifact of how your visual system processes the sequence. Space-time, in the four-dimensionalist picture, is the strip. The frames are the temporal parts. And the projection, the felt passage from one frame to the next, is consciousness, reading the structure from the inside, one slice at a time. You do not move through time. Time is a dimension you are extended along. The feeling of moving is the internal perspective of a shape that has no external motion. Hermann Minkowski did not begin with philosophy. He began with the mathematics of Einstein's relativity. In 1905, Einstein had shown that the speed of light is the same for all observers, regardless of their motion. This constancy forced a radical rearrangement of the concepts of space and time. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. Time intervals dilate, spatial lengths contract. But something remains invariant, a particular combination of space and time coordinates, a quantity Minkowski called the space-time interval. The interval between two events is given by the equation s² equals -c²t² plus x² plus y² plus z². Here c is the speed of light, t is the time separation between the events, and x, y, z are the spatial separations. The interval s is the same for every observer, no matter how they are moving. It is the true geometric distance in space-time, the quantity all observers agree on, even though they disagree about the individual space and time components. This invariance revealed the structure beneath relativity. Space and time are not absolute, but space-time is. The universe is not a three-dimensional space evolving through a separate time. It is a four-dimensional continuum, a fixed geometric structure in which every event has a definite location, a set of four coordinates specifying where and when it occurs. Minkowski wrote this structure as a metric, a rule for measuring distances in spacetime. The Minkowski metric, in its simplest form, is a diagonal matrix, -1 for time, +1 for each of the three spatial directions. The minus sign is what distinguishes time from space. Even in a static block, time is not just another dimension like width or height. It is geometrically different, and that difference is encoded in the metric. But the metric also encodes something else, the impossibility of a universal now. In Newtonian physics, simultaneity is absolute. If two events happen at the same time for one observer, they happen at the same time for all observers. But in Minkowski spacetime, simultaneity is relative. Two events that are simultaneous in one reference frame are not simultaneous in another frame moving relative to the first. The now you experience, the set of events you consider to be happening at this moment, is a space-like hypersurface through spacetime, a three-dimensional slice. But that slice is not unique. A different observer, moving past you, slices spacetime along a different angle and experiences a different now. This relativity of simultaneity is not a minor technical detail. It is the core of the argument for eternalism, the view that past, present, and future are equally real. If there is no observer-independent present, then there is no ontological distinction between now and then. The future exists in exactly the same sense the past does. It is already there, waiting in the space-time block, even though you have not yet reached the temporal parts that will experience it. The argument was formalized in the 1960s by two philosophers, C.W. Reitdijk and Hilary Putnam. Reitdijk published first in 1966. Putnam followed in 1967 with a paper titled Time and Physical Geometry. The reasoning is straightforward. Suppose two observers, Alice and Bob, are moving relative to each other. Alice considers event X to be in her future. But due to the relativity of simultaneity, Bob, moving past Alice, considers event X to be in his present. If Bob's present is real and simultaneity is relative, then Alice's future must also be real, because Bob's present includes events that are, from Alice's perspective, not yet happening. Putnam wrote, "Any future event X is already real." The logic seemed inescapable. Special relativity forces you to accept that different observers carve spacetime into now in different incompatible ways. If all those nows are equally valid, and if what exists in someone's now must be real, then everything, past, present, future, must exist equally. The philosopher Roger Penrose illustrated this with a thought experiment now called the Andromeda-paradox. Imagine two people walking past each other on a sidewalk. One is walking in one direction, the other in the opposite direction. The Andromeda galaxy is 2.5 million light-years away, roughly 9.5 quintillion miles. At this moment, from the perspective of the first person, events in Andromeda are unfolding in their present. But due to the walker's relative motion, their planes of simultaneity are tilted with respect to each other. From the perspective of the second person, walking in the opposite direction, the events in Andromeda that are happening now are offset by several days into the first person's future. Two people walking at a few miles per hour, slicing the distant galaxy into different presents, separated by days. If both slices are real, if simultaneity is merely a matter of reference frame, then the future days are already as fixed and determinate as the past ones. The fleet has already launched, or it has not launched yet, depending only on which walker you ask. But the launch itself, as an event in space-time, does not care which walker is asking. It exists at a specific set of coordinates, and both walkers' world lines will eventually intersect the light cone of that event. The difference is only in when they label it now. This is the block universe. Every event that has ever occurred, is occurring, or will occur, exists as a fixed point in the four-dimensional manifold. The Big Bang is there. Your birth is there. This moment, reading these words, is there. Your death is there. All of it laid out in a completed structure, with no ontological distinction between past, present, and future, except the one imposed by your location within it and the direction your consciousness is oriented. And if the block universe is the correct description, then nothing moves. Movement, in the intuitive sense, requires a present that advances, a now that slides forward in time, carrying objects along with it. But there is no advancing present. There is only the static geometry and your awareness reading one temporal part after another, creating the illusion of motion as it goes. Think about a surveyor standing on a hillside with a theodolite. The surveyor measures the slope of the ground, the angle it makes relative to the horizontal. The ground itself does not move. The slope is an intrinsic geometric property, a feature of the surface's shape. A steep slope, a gentle slope, a flat plane. These are static facts about the geometry. Velocity in spacetime is a slope. The world line of an object at rest is vertical, parallel to the time axis. The world line of an object moving at constant velocity is tilted, angled through both space and time. The greater the velocity, the steeper the tilt. But the world line itself is static. It does not move through space-time any more than the hillside moves through the landscape. The shape is fixed. What changes is which temporal part of the world line you are looking at. And what you are looking at is determined by your own position in space-time. You are not a point moving along your world line. You are the world line, extended from birth to death, and the you that feels like it is moving is a particular temporal part, a cross-section, embedded in the structure. That temporal part has memories of earlier temporal parts, and it anticipates later temporal parts, and the continuity of those memories and anticipations is what generates the feeling of being a single, persisting self. But the self that persists is not a thing that travels. It is a four-dimensional worm, and the traveling is the shape of the worm itself. David Lewis, the philosopher who did more than anyone to formalize this view, called it the problem of temporary intrinsics. Here is the problem. You sit down and you are bent. You stand up and you are straight. How can you be both bent and straight? In ordinary language, we say you are bent at one time and straight at another. But bent and straight are intrinsic properties, properties the object has in itself, not in relation to anything else. If you are a single three-dimensional object, wholly present at each moment, then you cannot possess contradictory intrinsic properties. You cannot be both bent and straight. The solution, Lewis argued, is that you are not wholly present at each moment. You are a four-dimensional worm, and the worm has temporal parts. The temporal part of you at 10:30, sitting, is bent. The temporal part of you at 10:31, standing, is straight. Each part has its properties intrinsically, without contradiction, because they are different parts. Change is not a single object altering its properties over time. Change is the possession of different properties by different temporal parts of the same four-dimensional object. Lewis wrote, "When I sit, I'm bent. When I stand, I'm straight." The solution is that I am not a single three-dimensional thing. I am the sum of my temporal parts, and the sitting me and the standing me are distinct slices of that sum. This is perdurantism, the view that objects persist by perduring, by having temporal parts spread across time. It is distinguished from endurantism, the view that objects endure, that they are wholly present at each moment, with no temporal parts at all. For the endurantist, you are a three-dimensional entity that exists entirely at each instant, and the properties you have are indexed to times, or held relative to times, not distributed across parts. The perduranist denies this. You do not exist entirely at any instant. You exist as a temporally extended whole, and what exists at an instant is only a part of you. A third view, called stage theory, goes even further. Theodore Sider, building on Lewis, argued that ordinary objects are the instantaneous stages themselves, not the four-dimensional worms. You, right now, are a momentary stage, and persistence is handled by a temporal counterpart relation. Future stages are your counterparts, connected by continuity of properties and causal relations. But they are not literally parts of you. They are other things, related to you in the way that possible world counterparts are related in Lewis's modal realism. The stage theorist says, "I will survive this," is true not because a future temporal part of me exists, but because a future stage, suitably related to this stage, will exist. The distinctions here are subtle, and some philosophers treat them as merely verbal. But the underlying commitment is the same, the view that objects, including persons, are structures in space-time, not travelers through it. Whether you are the whole worm or a single stage, the geometry is static. Motion is shape. And if motion is shape, then the flowing present, the feeling that time passes, that moments arrive and then slip into the past, is not a feature of time itself. It is a feature of how you, as a temporal part or stage, register the structure you are embedded in. Your brain constructs a present, it does not perceive one. In the summer of 2007, a team of neuroscientists at Caltech conducted an experiment involving a free fall drop and a perception of duration. Subjects were taken to a SCAD tower, a structure used for stunt training, where they would fall 31 meters into a safety net. The fall lasted about 2.5 seconds. On their wrist, each subject wore a custom device called a perceptual chronometer, which flashed numbers at a rate just fast enough that the numbers blurred together and could not be read under normal conditions. The idea was that if the fall genuinely caused time to slow down, if the brain's clock sped up, allowing more perceptual processing per unit of real time, then the subjects would be able to read the numbers during the fall. They could not. Not a single subject could read the chronometer. The flashing rate remained above their perceptual threshold throughout the fall, exactly as it did when they stood on solid ground. But when the researchers asked the subjects to estimate how long their own fall had lasted, compared to how long they had watched other subjects fall, the estimates diverged. On average, the subjects judged their own fall to be 36% longer than others' falls. 36%. A 2.5-second event, remembered as feeling like more than 3 seconds, with no increase in temporal resolution. The slow-motion experience of terror is a memory artifact, not a perceptual reality. The lead author of the study, David Eagleman, summarized the finding. Participants retrospectively estimated their own fall to last 36% longer than others' falls, but when tested, their ability to perceive fine temporal detail, to resolve rapid sequences, showed no improvement. The brain was not processing information faster during the fall, it was writing the memory more densely, encoding the fear and the salience of the event in a way that, when recalled later, felt stretched in time. The conscious experience of duration is constructed after the fact. This is not an isolated finding, it is part of a broader pattern in neuroscience. The present you experience is not the present as it occurs. It is a model, assembled by the brain from sensory data that arrive at different times and are processed at different speeds. In the 1960s and 70s, a neuroscientist named Benjamin Libet conducted a series of experiments that revealed a profound delay between neural activity and conscious awareness. Libet applied direct electrical stimulation to the somatosensory cortex of patients undergoing brain surgery, and he measured how long it took for them to report feeling the stimulation. The patients were awake and could describe what they felt. Libet found that a minimum of about 500 milliseconds of continuous neural activity was required before the patient reported conscious sensation. 500 milliseconds, half a second. A single evoked potential, a neural response to a stimulus, occurs in about 15 milliseconds. A spinal reflex takes about 100 milliseconds. But conscious awareness requires a sustained process lasting half a second. The stimulus happens, the neural response begins, and then, hundreds of milliseconds later, after the brain has accumulated enough activity, you become aware of it. And even that awareness is retrospectively antedated. Libet found that when patients did become conscious of the stimulus, they did not feel it as happening half a second late. They felt it as happening roughly at the time the stimulus was applied. The brain back-projects the experience, assigning it to an earlier moment in subjective time, to align the conscious experience with the actual event. This backshadowing, as it is sometimes called, is a form of post-diction, the brain reconstructing the sequence of events after they have already occurred, and presenting the reconstruction as if it were the original perception. Eagleman, along with his colleague Terence Sejnowski, coined the term in a 2000 paper in the journal Science, studying motion perception. They found that the perceived position of a moving object is influenced by information arriving up to 80 milliseconds after the object's actual position changes. The brain uses data from the near future to determine what you saw in the near past. The present is assembled, not perceived. Mark Whitman, a psychologist at the Institute for Frontier Areas of Psychology in Freiburg, has studied the neural basis of subjective time for decades. In his book Felt Time, published in 2016, Whitman reviews the evidence that temporal experience is constructed by the brain's integration of multiple sensory streams, bodily states, and memory systems. The insula, a region of the cortex involved in interoception, the sensing of the body's internal state, plays a central role. Time feels like it is passing because the brain is continuously updating its model of the body's condition, and the rate of that updating generates the feeling of duration. Whitman distinguishes several layers of temporal awareness. The shortest is the functional moment, lasting about 30 to 300 milliseconds, the window within which sensory events are integrated into a single percept. Then there is the experienced or specious present, typically lasting 2 to 3 seconds, the duration over which you feel a continuous now. This is the window in which a spoken sentence, a musical phrase, or a gesture is perceived as a single event. Beyond that is the integration of the present with memory and anticipation, which can extend over minutes or hours. But none of these layers are the true present. They are all constructions assembled from data that arrived in the past, processed by systems that take time to operate, and projected into a subjective timeline that does not map directly onto the physical timeline. Dean Buonamano, a neuroscientist at UCLA, puts it this way in his book, Your Brain is a Time Machine. In practice, neuroscientists are implicitly presentists. The brain makes decisions in the present based on the memories of the past to enhance our well-being in the future. The brain treats the present as if it is a single, definite, moving point. But the present it treats that way is a model, lagging behind reality by up to half a second, post-dictively adjusted and smoothed over to hide the seams. If the present is constructed, then the passage of time, the feeling that moments flow from future to present to past, is also constructed. It is a narrative your brain tells itself to make sense of the changing patterns in the sensory and memory data it processes. But the narrative is not the territory. The map is not the landscape. Craig Callender, a philosopher of physics at UC San Diego, has argued that our intuitive conception of time, what he calls manifest time, is radically disconnected from the time described by physics. In his book, What Makes Time Special, Callender writes, "Our best science of time suggests that manifest time is more or less rubbish. The flowing present, the sharp distinction between past and future, the sense that the past is fixed and the future is open, all of these features of manifest time are absent from the spacetime of relativity. What physics gives us is a four-dimensional block, sliced in different ways by different observers, with no privileged present and no objective flow." Callender proposes that manifest time is the product of what he calls an IGUS, an information gathering and using system. An IGUS is embedded in the world, receiving sensory data, storing memories, making predictions, and acting on its environment. The asymmetries we associate with time, memory of the past but not the future, causation from past to future, the increase of entropy, are all features of how an IGUS interacts with the thermodynamic gradient of the universe, not features of time itself. An IGUS, in other words, is a temporal part reading its neighbors. The flow it feels is the internal perspective of a static structure, processing information in a thermodynamically asymmetric way. Donald Hoffman, a cognitive scientist at UC Irvine, takes this further. In his book, The Case Against Reality, Hoffman argues that perception in general, not just the perception of time, but the perception of space, objects, and causation, is not shaped to reveal truth. It is shaped to enhance fitness. Evolution shapes perceptual systems to detect what matters for survival and reproduction, not what is objectively real. A frog does not perceive flies as they truly are. It perceives fly-like features that trigger a tongue strike reflex. The features are useful, but they are not veridical. Hoffman calls this the interface theory of perception. Perception is an interface, like the desktop icons on a computer screen. The icon of a trash can does not look like the transistors and voltage patterns that represent deleted files in the computer's memory. The icon is a simplified, user-friendly representation, shaped to make interaction easy. When you drag a file to the trash, you are manipulating the interface, not the underlying reality. But the manipulation works, and that is all evolution cares about. Space-time, Hoffman argues, is your desktop. Physical objects are icons. Neurons, atoms, quantum fields, all of it is part of the interface, not the reality behind it. The reality, he proposes, is a network of conscious agents, interacting according to mathematical rules that have nothing to do with space or time. Space-time is a data structure, evolved to compress the complexity of that network into a manageable perceptual format. Motion, in this view, is an icon. The feeling that objects move through space over time is a perceptual shorthand, shaped by evolution to track useful patterns in the agent network, but with no correspondence to the underlying ontology. The block universe is still an interface, a more accurate one than manifest time, but still a map, not the territory. What does it mean that the present you are experiencing right now, the moment you feel yourself to be in, is a construction lagging half a second behind physical reality, assembled from postdictive stitching and memory back projection. What does it mean that the flow you feel, the passage from one moment to the next, is a narrative your brain tells itself to organize sensory and memory data, not a feature of the space-time you are embedded in? It means that when you see motion, a car driving past, a pendulum swinging, your hand moving across a table, you are not seeing an object changing position in real time. You are seeing a model, constructed from delayed and postdictively adjusted data, projected onto a perceptual timeline that does not correspond to the physical one. The motion is in the model, not in the world. And if the motion is in the model, then the question is, what is in the world? In 1971, the year Joseph Hafele and Richard Keating flew atomic clocks around the planet, the clocks spent a combined total of about 6 days in the air. The clocks themselves were HP 5061, a cesium beam clocks, the most precise timekeepers available at the time. Each clock had its own airline ticket. Each clock had its own seat. The experiment cost roughly $8,000, funded by the Office of Naval Research. The eastward trip began on October 4th. The clocks flew from Washington to London, to Beirut, to Tehran, to New Delhi, to Bangkok, to Hong Kong, to Tokyo, to Honolulu, and back to Washington. Total flight time, about 41 hours. The westward trip began on October 13th, following the reverse route. Total flight time, about 49 hours. When the clocks returned, they disagreed with the ground clocks. The eastward flying clocks had lost time, lagging behind by an average of 59 nanoseconds, plus or minus 10. The westward flying clocks had gained time, running ahead by an average of 273 nanoseconds, plus or minus 7. The predictions from general relativity were minus 40 nanoseconds for the eastward trip and plus 275 nanoseconds for the westward trip. The measurements matched the predictions to within the experimental uncertainty. This was not a test of whether clocks slow down at high altitude or speed. It was a test of whether time itself slows down. The clocks were measuring proper time, the time experienced along their own world lines. The ground clocks were measuring proper time along the world line of the Earth's surface. The world lines diverged, curved through space-time along different paths, and accumulated different amounts of elapsed time. When the world lines reconverged, the clocks disagreed. There is no universal now. There is no single objective present that all observers share. The simultaneity surface, the set of events you consider to be happening at this moment, is a feature of your reference frame, not a feature of space-time itself. A different observer, moving relative to you or at a different gravitational potential, slices space-time differently and experiences a different now. The hafele-keating experiment made this measurable. Two clocks, initially synchronized, following different paths through space-time, reading different proper times when they meet again. The difference is tiny, nanoseconds, but it is real. And if time can disagree by nanoseconds over a 3-day flight, it can disagree by much more over longer durations or higher velocities. Every GPS satellite orbits at an altitude of about 20,000 kilometers, roughly 12,400 miles, moving at about 1,900 meters per second, roughly 4,200 miles per hour. At that altitude, the gravitational time dilation causes the satellite's clock to run faster than a clock on the ground by about 45 microseconds per day. At that velocity, the kinematic time dilation causes the satellite's clock to run slower than a clock on the ground by about 7 microseconds per day. The net effect is that the satellite's clock gains about 38 microseconds per day relative to the ground. 38 microseconds per day. If the GPS system did not correct for this, the position error would grow by about 10 kilometers, 6 miles, every day. The system would be useless within hours. The correction is built into the satellite's firmware. The satellite's clock is deliberately set to run slower than the frequency it would naturally run at, so that when the relativistic effects are applied, it synchronizes with the ground clocks. The system works because the engineers who built it treated spacetime as a four-dimensional geometry with a metric that depends on position and velocity, and they calculated the proper time along each satellite's world line relative to the ground. Every GPS receiver in your phone or your car is a practical demonstration that there is no universal present. The satellite's clocks and the ground clocks do not agree on how much time has passed since their world lines diverged. The synchronization is frame-dependent, and the system accounts for that. The now on the satellite and the now on the ground are not the same. They are different space-like hypersurfaces through the space-time block, tilted with respect to each other, intersecting different sets of events. If simultaneity is relative, then the present is not a global fact. It is a slice chosen by a reference frame. And if the present is not a global fact, then the distinction between what is happening now and what will happen later is not an ontological distinction. It is a perspectival distinction, like what is to the left of me versus what is to the right of me. The events to your left and the events to your right all exist in space. They are distinguished only by their relation to your position and orientation. In the same way, the events in your past and the events in your future all exist in space-time. They are distinguished only by their relation to your world line and the time-like direction you are oriented along. This is the core of the Retrocausality argument. If there is no observer-independent present, then there is no observer-independent distinction between what is real now and what is not yet real. If Bob's now includes events that Alice considers to be in her future, and Bob's now is as valid as Alice's, then Alice's future is as real as Alice's present. The future is already there, waiting in the block, even though Alice has not yet experienced the temporal parts of herself that will intersect it. But there is a counter-argument. The philosopher Howard Stein, writing in 1968 and again in 1991, pointed out that the Retrocausality inference is not airtight. Stein showed that even in special relativity, there is a meaningful notion of the past and future relative to an event. The past of an event is the set of events in its backward light cone, the events that could have causally influenced it. The future of an event is the set of events in its forward light cone, the events it could causally influence. The elsewhere is the set of events outside both cones, events that are space-like separated from the event, neither in its causal past nor its causal future. Stein argued that what is real relative to an event can be defined as the union of its past light cone and the event itself. The future light cone remains open, not in the sense that it does not exist in space-time, but in the sense that it is not yet determined by anything in the event's causal past. This gives you a version of the open future that is compatible with special relativity. The future exists as a region of space-time, but it is not determined by the present in the way the past is determined. The distinction between past and future is not erased by the relativity of simultaneity. It is preserved in the structure of the light cones. Whether Stein's argument rescues presentism or merely shows that eternalism does not follow deductively from relativity is a matter of debate. What is not debatable is that the clocks disagree. Time bends. The present is frame-dependent, and any account of motion that relies on a universal, flowing now, a single present moment sliding forward, carrying objects along with it, is incompatible with the measurements. If motion requires a moving present, and the present does not move, then motion, as intuitively conceived, does not exist. In April 2004, NASA launched a satellite called Gravity Probe B. The mission's goal was to test two predictions of general relativity with unprecedented precision. The geodetic-effect, which describes how space-time curvature near a massive body causes a gyroscope's axis to drift, and the frame-dragging effect, which describes how a rotating massive body drags space-time itself into rotation around it. The satellite carried 4 gyroscopes, each a quartz sphere coated in niobium and cooled to 1.8 Kelvin, spinning at about 70 revolutions per second. The spheres were nearly perfect. Deviations from perfect roundness were less than 40 atomic layers. The satellite orbited Earth at an altitude of about 640 kilometers, roughly 400 miles, in a polar orbit that passed over the poles every 97 minutes. The mission lasted 17 months. The gyroscopes pointed at a guide star, IM Pegasi, and the scientists measured how the gyroscope's spin axes drifted relative to the star's position. The drift was tiny, measured in milliarc-seconds per year. 1 milliarc-second is about 1/200th the width of a human hair seen from a kilometer away. The geodetic effect, caused by the curvature of space-time around Earth's mass, was predicted to cause a drift of minus 6,606.1 milliarc-seconds per year. The measured drift was minus 6,601.8, plus or minus 18.3 milliarc-seconds per year. Agreement within 1/10 of 1%. The frame dragging effect, caused by Earth's rotation, was predicted to cause a drift of minus 39.2 milliarc-seconds per year. The measured drift was minus 37.2, plus or minus 7.2 milliarc-seconds per year. Agreement within 5%. Frame dragging is the phenomenon where a rotating mass twists spacetime around it, so that objects near the mass are dragged into co-rotation, even if they are not physically touching the mass. The effect is extraordinarily weak near Earth. A gyroscope in orbit drifts by less than 40 milliarc-seconds per year, a drift so small that detecting it required gyroscopes accurate to a billionth of a degree and 17 months of continuous measurement. But the effect is real. Spacetime is not a static stage. It is a dynamic geometry, shaped by mass and energy, and near a rotating mass, the geometry itself rotates. The most extreme case of frame dragging occurs near a rotating black hole. The geometry is described by the kerr-metric, derived by the New Zealand mathematician Roy Kerr in 1963. The kerr-metric describes a black hole with mass m and angular momentum j. The angular momentum is parameterized by a, where a equals j divided by mc, and c is the speed of light. For a non-rotating black hole, a is 0, and the kerr-metric reduces to the Schwarzschild metric. For a maximally rotating black hole, called an extremal Kerr black hole, a equals m. Around a Kerr black hole, there is a region called the ergosphere. The ergosphere is bounded by two surfaces. The inner boundary is the event horizon, the surface of no return. The outer boundary is the static limit, also called the ergosurface. The ergosurface is defined by the condition that the time translation killing vector, the geometric object that represents staying at a fixed spatial position, becomes space-like. Outside the ergosurface, it is possible to remain stationary relative to a distant observer. Inside the ergosurface, it is not. The reason is that inside the ergosphere, frame dragging is so strong that every Timelike world line, every possible trajectory of a physical object, is dragged into co-rotation with the black hole. You cannot stand still. The geometry does not permit it. Standing still would require a space-like world line, which corresponds to faster-than-light travel, which is forbidden. Every future-directed time-like curve necessarily has a non-zero rotational component in the azimuthal direction. You are forced to rotate not by any physical force acting on you, but by the shape of spacetime itself. Naresh Dadich, in a 2015 paper on the Archive, wrote, "A particle cannot remain fixed at a point, it has to rotate." The static limit marks the boundary where staticity becomes impossible. This is motion as pure geometry. No force pushes you, no engine accelerates you. The world line you follow is a geodesic, a free-fall path, the straightest possible curve through the curved spacetime. But that curve is tilted azimuthally because the spacetime itself is rotating. The motion is encoded in the metric, in the off-diagonal components that mix time and the angular coordinate, and what you experience as being forced to rotate is simply your world line conforming to the only time-like directions the geometry allows. In 1969, Roger Penrose realized that the ergosphere allows a form of energy extraction. A particle can enter the ergosphere, split into two fragments, and one fragment can fall into the black hole along a trajectory with negative energy, as measured by a distant observer, while the other fragment escapes with more energy than the original particle had. The escaping fragment has extracted rotational energy from the black hole, at the cost of reducing the black hole's angular momentum. The maximum efficiency of a single Penrose process for an extremal Kerr black hole is about 20.7%. Up to 29% of the black hole's total mass energy is extractable rotational energy stored in the spin. The irreducible mass, the part that cannot be extracted, is about 71%. This energy is not hidden inside the event horizon. It is stored in the geometry of the ergosphere, in the way the spacetime is twisted. The Penrose process is a thought experiment, never observed and likely impractical to implement. But it illustrates the principle. Energy, momentum, and motion are geometric properties of spacetime, not substances flowing through it. The black hole does not have angular momentum in the sense of containing a spinning object. The angular momentum is the shape of the spacetime, the degree to which the metric mixes time and azimuthal angle. Extracting the energy is equivalent to flattening the geometry, reducing the twist, lowering the value of A. What does it mean that inside an ergosphere, standing still is geometrically impossible? It means that motion is not something you do, it is something the world line already is, determined by the metric. And if that is true in the extreme case of the ergosphere, where the geometry is so warped that the conclusion is unavoidable, then it is also true in the ordinary case of walking across a room, where the geometry is nearly flat and the twist is imperceptible. The difference is only quantitative. The structure is the same. In 1949, Kurt Gödel, Einstein's colleague at the Institute for Advanced Study in Princeton, discovered a solution to Einstein's field equations that described a rotating universe. The Gödel universe is filled with a uniform density of matter, and the matter is rotating as a whole. The rotation rate is given by omega equals twice the square root of pi times g times rho, where rho is the matter density and g is Newton's gravitational constant. In the Gödel universe, every observer sees themselves at the center of the rotation. The matter around them is rotating, but there is no axis. The rotation is global, not around a point. And because the universe is rotating, space-time is twisted in such a way that there exist closed time-like curves, world lines that loop back on themselves, returning to the same space-time event they started from. A closed time-like curve is a path through space-time that, if followed, brings you back to your own past. You could, in principle, meet yourself at an earlier time. The grandfather paradox, the logical problem of going back in time and preventing your own existence, becomes a real feature of the geometry, not a science fiction fantasy. Gödel's universe does not describe our universe. Our universe is expanding and, on large scales, approximately homogeneous and isotropic, not rotating. But the Gödel solution is a valid solution to Einstein's equations, and it demonstrates that closed time-like curves are not forbidden by the laws of general relativity. They are geometrically possible. Whether they are physically possible is an open question. Stephen Hawking proposed a chronology protection conjecture, which states that the laws of physics prevent the formation of closed time-like curves except in pathological cases like the Gödel universe. The conjecture has never been proven, and there is no consensus on whether it is correct. Other routes to closed time-like curves have been proposed. Kip Thorne and his colleagues showed in 1988 that a traversable wormhole, if it existed, could be turned into a time machine by accelerating one mouth relative to the other. The relative motion causes a time dilation between the two mouths, and once the dilation is large enough, a path through the wormhole becomes a closed, time-like curve. But traversable wormholes require exotic matter with negative energy density, and there is no evidence that such matter exists in the quantities required. David Deutsch, a physicist at Oxford, proposed in 1991 a quantum model of closed, time-like curves that avoids the paradoxes by treating the state of the system as a self-consistent fixed point. In Deutsch's model, the state of a particle entering the CTC is a mixed state, a probabilistic superposition, chosen such that when the particle loops back to the past, it is consistent with the state it had when it entered the loop. The grandfather paradox is resolved not by forbidding the action, but by finding a quantum state in which the action is self-consistent. You can interact with your past self, but only in ways that do not generate a logical contradiction. Igor Novikov, in his book The River of Time, formulated what is now called the Novikov self-consistency principle. Events on a closed time-like curve are constrained to be globally self-consistent. If you travel back in time, you cannot kill your grandfather, not because you are prevented by some external force, but because the only world lines that form closed loops are the ones where you fail to kill him, or where the person you kill turns out not to be your biological grandfather, or where some other detail resolves the paradox. The universe, in this view, is a four-dimensional block with closed, time-like curves woven into it, and the events on those curves are self-consistently fixed. What does it mean to be a self on a closed world line? If your world line loops back to an earlier time, are you a single continuous worm, or are you two separate stages occupying the same event? The question is not well formalized. The identity conditions for spacetime worms were developed for open, non-looping world lines, and they do not straightforwardly extend to the closed case. Derek Parfit, in his 1984 book Reasons and Persons, argued that personal identity is not what matters for survival and moral responsibility. What matters is psychological continuity and connectedness, what Parfit called the R relation. If a later person stage has memories of an earlier person stage, and if the two stages are connected by a chain of overlapping psychological states, beliefs, desires, intentions, character traits, then the later stage stands in the R relation to the earlier one, and that is sufficient for the kind of persistence that matters morally. Parfit illustrated this with thought experiments involving fission and teletransportation. Suppose your brain is divided into two hemispheres, and each hemisphere is transplanted into a different body. Both resulting persons have memories of being you, and both are psychologically continuous with you. Are you identical to both of them? You cannot be, because identity is a one-to-one relation, and they are two. Parfit's answer is that identity is not what matters. What matters is the R relation, and you stand in the R relation to both of them. You survive as both, even though you are not identical to either. Or suppose you step into a teletransporter, which scans your body, transmits the information to Mars, and reconstructs an exact physical duplicate of you there, while destroying the original. The duplicate on Mars has all your memories, your personality, your dispositions. Is the duplicate you? Parfit argues that if you accept that the R relation is what matters, then the duplicate is you in the only sense that matters. The fact that there is a discontinuity in the physical continuity of your matter is irrelevant. The person on Mars stands in the R relation to the person who stepped into the scanner, and that is sufficient for survival. For a perdurantist, these cases are straightforward. The person who steps into the scanner is a temporal part of a space-time worm. The person who emerges on Mars is another temporal part. If the two parts are connected by the R relation, then they are parts of the same worm, or at least counterparts in the stage theorist's sense. The worm can branch, just as a river can fork into two streams. Identity in the strict sense may not survive branching, but the R relation does, and the R relation is what matters. For an endurantist, the cases are harder. If you are wholly present at each moment, and if identity is a primitive, non-reducible relation, then either you survive the teletransportation or you do not. There is no middle ground. And if the answer is that you do not survive, that the person on Mars is a duplicate, not you, then the teletransportation is a form of death, even though no one can tell the difference from the outside. The closed time-like curve adds another layer. Suppose you enter a CTC, loop back to an earlier time, and meet your younger self. Are the two of you identical? You are the same person at two different stages, but the stages exist simultaneously in the loop. The younger stage has not yet experienced the journey that the older stage has completed. The older stage remembers being the younger stage, but the younger stage does not yet remember being the older stage. The R relation is asymmetric, running only one direction around the loop. Theodore Sider has argued that the notion of a person or a self is conventional, not metaphysically deep. The space-time worm is the fundamental entity. How you carve the worm into persons, stages, or temporal parts is a matter of pragmatic choice, not ontological fact. The worm itself is just there, a four-dimensional region of space-time with certain physical properties distributed across it. Calling it one person or two persons or a person at two times is a way of organizing the facts, not a discovery about what exists. This deflationary view is resisted by many philosophers who argue that personal identity is too important, morally, legally, emotionally, to be merely conventional. But if the perdurantist picture is correct, and if objects are worldtubes with no privileged now sliding along them, then the self you feel yourself to be, the unified, persisting I, is a construction, assembled by the brain from memories and anticipations, projected onto a worm that has no intrinsic unity beyond the causal and psychological connections between its parts. You are not a thing that travels through time. You are a shape in time, and the traveler is an illusion generated by one cross-section of the shape reading its neighbors. In 2012, Frank Wilczek, a Nobel laureate in physics, published a paper in Physical Review Letters titled Quantum Time Crystals. The paper proposed the existence of a new phase of matter, a system that, in its ground state, exhibits periodic structure not in space, but in time. Ordinary crystals exhibit spatial periodicity. The atoms in a crystal lattice are arranged in a repeating pattern, and the pattern extends across space. The periodicity breaks spatial translation symmetry. If you shift the crystal by a small amount, it does not look the same. But the crystal is in its ground state, the state of lowest energy. It is static. The atoms do not move. A time crystal, as Wilczek envisioned it, would exhibit temporal periodicity in its ground state. The system would oscillate, repeating the same configuration at regular intervals, without any external driving force. This would break time translation symmetry. If you shift the system forward in time by a small amount, it does not look the same. But like a spatial crystal, it would be in an eigenstate, a quantum state with definite energy. The proposal was controversial. Several physicists quickly published rebuttals. In 2013, Patrick Bruno argued that a time crystal in its ground state would constitute perpetual motion, violating the laws of thermodynamics. In 2015, Masaki Oshikawa and Haruki Watanabe proved a no-go theorem. A time crystal in a true ground state in thermal equilibrium is impossible. But Wilczek's idea was not entirely dead. The key was to relax the requirement that the system be in equilibrium. In a non-equilibrium setting, driven by an external periodic force, a system can exhibit a kind of temporal order called discrete time translation symmetry breaking. The system responds to the driving force, but it does so at a frequency that is a fraction of the driving frequency, typically half. The system locks into a periodic orbit that persists indefinitely, even in the presence of disorder and decoherence, and the periodicity is a property of the system's many-body quantum state, not just a response to the driving. This is the discrete time crystal, and in 2021, a team at Google, working with the Sycamore quantum processor, demonstrated one experimentally. The experiment, published in Nature, used a chain of 20 qubits, isolated from the rest of the 53-qubit array. The qubits were driven by a sequence of microwave pulses that flipped their states and induced interactions between neighbors. The sequence repeated every 2 time steps. The system responded at half the driving frequency. If the driving had a period of t, the system oscillated with a period of 2t. This subharmonic response persisted for hundreds of cycles, far longer than the decoherence time of the individual qubits. The time crystalline order was robust, protected by the collective behavior of the many-body system. Vedika Kamani, a physicist at Stanford who co-conceived the phase, and Pedram Rushan, a senior author at Google, showed that the system exhibited a genuine quantum phase of matter, distinct from a simple driven oscillator. The periodicity was not imposed by the driving, it was an emergent property of the system's quantum state, a form of spontaneous symmetry breaking in time. Does this prove that time has discrete parts? No. The time crystal breaks discrete time translation symmetry, the symmetry undershifts by integer multiples of the driving period. It does not prove that time itself is discrete, or that the system occupies distinct, non-overlapping temporal parts in the perdurantist sense. The system evolves continuously in time, governed by the Schrödinger equation, and the periodicity is a feature of the system's state as a function of time, not evidence that time is composed of atomic moments. But the time crystal does reveal something: that temporal structure can be intrinsic to a system's quantum state, not merely imposed by external dynamics. The system has a preferred period, a timescale that is not set by the driving frequency, but by the interactions and disorder within the system. In that sense, the time crystal is a hint that time, even in quantum mechanics, is not just a parameter. It is something the system organizes itself around. And if a quantum system can spontaneously break time translation symmetry, organizing its state into periodic structure that persists without equilibrium, then time is not as featureless as the classical block universe suggests. There is room for structure, for asymmetry, for something like a preferred direction or a preferred frequency. Whether that structure supports a genuine A-theory of time, a theory in which passage and presentness are objective, is still unresolved. But it suggests that the block is not the end of the story. Julian Barbour, a British physicist who has spent decades working on the foundations of time and motion, takes the opposite view. Barbour argues that time is not just featureless, it is an illusion. In his 1999 book, The End of Time, and his 2020 follow-up, The Janus Point, Barbour constructs a theory in which time does not exist as a fundamental entity. What exists is a space of possible configurations, which he calls Platonia. Platonia is the configuration space of the universe, the set of all possible spatial arrangements of matter. Each point in Platonia is a now, a complete, instantaneous three-dimensional configuration of everything in the universe. The nows are static. They do not evolve. There is no time parameter carrying them from one configuration to another. What we perceive as time, Barbour argues, is the structure within individual nows. Some nows contain records, fossils, memories, documents, tree rings, light from distant stars. These records generate the appearance of a past, but the past they point to is not real. The past is not a set of earlier nows that actually existed, it is a pattern within this now, a structure that encodes information in a way that feels like memory. Barbour calls these records time capsules. You are a time capsule. Your brain contains memories that feel like they refer to earlier moments in your life. But those earlier moments are not real events that occurred in a sequence. They are patterns within the current now, and the feeling of having lived through them is an illusion generated by the structure of the patterns. In Barbour's picture, each now exists independently, and the universe is the totality of all nows in Platonia. There is no motion because there is no sequence. There is no earlier or later, only a vast space of possible configurations, each equally real, each containing its own internal records that generate the illusion of a history. Barbour also developed, with Tim Kozlowski and Flavio Mercati, a proposal called shape dynamics, which attempts to replace general relativity with a theory based purely on relational geometry. In shape dynamics, space and time as absolute entities are eliminated. What remains is a sequence of shapes, three-dimensional geometries that specify the relative positions of objects, without reference to an external spacetime. The theory predicts a special configuration in the history of the universe, which Barbour calls the Janus point. The Janus point is the moment of minimal complexity, the configuration from which complexity grows in both directions. In our universe, the Janus point would be near the Big Bang. But the growth is symmetric. The universe expands and becomes more complex as you move away from the Janus point in either temporal direction. There is no objective arrow of time, only the appearance of an arrow generated by our position relative to the Janus point. Shape dynamics is a minority program, and it has been criticized. H. Dieter Zeh, a pioneer of decoherence theory, wrote in 2016 that Barbour's Janus point arrow of time proposal appears trivial when considered in conventional terms, and far from being novel or realistic. The theory has not been developed to the point where it can fully recover general relativity, and it remains unclear whether it can serve as a viable route to quantum gravity. But Barbour's broader claim, that time is an illusion, is taken seriously by a subset of physicists. The Wheeler-DeWitt equation, the central equation of quantum cosmology, contains no time parameter. It is a constraint equation, describing the quantum state of the universe as a whole, without specifying how that state evolves. Barbour writes on his website, "This was by no means universally accepted among theoretical physicists at the time I wrote my book. It remains controversial. If time is an illusion, then motion is doubly so. Motion requires change, and change requires time. If there is no time, there is no motion. There are only configurations, some of which contain internal structure that resembles motion when viewed from the inside." And even if you reject Barbour's radical conclusion, even if you insist that time is real, the question remains, is motion something that happens, or is it something that is? Is the moving object genuinely crossing space, or is crossing merely the static shape of its world line, misread as dynamical flow by a consciousness embedded within it? The philosopher Craig Callender, reviewing the evidence, concludes that manifest time is largely rubbish. The flowing present, the sharp boundary between past and future, the sense that change is intrinsic and motion is real, all of these are features of how we, as IGUS, as information gathering and using systems, process the world. They are not features of the world itself. Donald Hoffman goes further. The world itself, as we perceive it, is not real. Spacetime is a user interface. The objects moving through it are icons. The motion is a perceptual shorthand, useful for survival, but bearing no resemblance to the underlying ontology. If they are right, then when you see your hand moving across the table, you are not seeing an object in motion. You are seeing a model, constructed by your brain, projected onto an interface, shaped by evolution to track fitness-relevant patterns, not to reveal truth. The motion is in the model, the world tube is in the spacetime, and the spacetime itself may be an interface, not the territory. What then is the territory? We do not know. Quantum mechanics offers a clue, though not a resolution. In standard quantum mechanics, the state of a system evolves in time according to the Schrödinger equation, which is deterministic and time-symmetric. The equation runs forward and backward with equal ease. But when a measurement is made, the state collapses to a definite outcome, and this collapse is irreversible and time-asymmetric. The future affects the present in a way the past does not. Yakir Aharonov, an Israeli physicist, has developed an interpretation of quantum mechanics that takes this time asymmetry seriously. In 1964, Aharonov, along with Peter Bergman and Joel Leibovitz, published a paper titled Time Symmetry in the Quantum Process of Measurement. The paper proposed the two-state vector formalism, which describes a quantum system at a particular time by two quantum states: the usual forward-evolving state, prepared in the past, and a backward-evolving state, post-selected in the future. The two-state vector formalism treats the future and the past as equally real inputs to the present. The state of the system at time t is not determined only by what happened before t. It is also determined by what will be measured after t. The present is a boundary between two temporal directions, both of which constrain what the present can be. In 1988, Aharonov, along with David Albert and Lev Vaidman, introduced the concept of weak values, which are quantum observables defined by both a pre-selected state, prepared in the past, and a post-selected state, measured in the future. The weak value of an operator A is given by the formula A sub W equals the quantum expectation value of A between the final state and the initial state, divided by the overlap of the final and initial states. Weak values can be strange. They can lie outside the range of eigenvalues of the operator. A spin measurement that can only return +1/2 or -1/2 can have a weak value of 100. The weak value is not the value the system has. It is a quantity that characterizes how the past and future states conspire to produce the measurement outcome. The two-state vector formalism has been described by Aharonov and his collaborators as leading to an admittedly controversial new view of the nature of time. The controversy is that the formalism is explicitly retrocausal. The future measurement affects the past weak value. The effect is not transmitted faster than light, and it does not allow signaling backward in time, but it does mean that the full description of the present requires information about both the past and the future. Hugh Price, a philosopher at Cambridge, and Ken Wharton, a physicist at San Jose State, have argued that retrocausality is the key to resolving the puzzles of quantum mechanics. In their view, quantum mechanics is best understood as an all-at-once constraint on the entire history of a system, not as a forward-evolving dynamics. The Lagrangian formulation of classical mechanics already treats the path of a particle as a solution to a boundary value problem, where the particle's trajectory is the one that extremizes the action over the entire interval. Quantum mechanics, in this view, is similar. The state of the system is a solution to a two-time boundary value problem, constrained by measurements at both ends. This is the Lagrangian schema for quantum mechanics, and it fits naturally with the block universe picture. If the future and the past are both real, both present in the completed spacetime block, then a law that refers to both ends of a temporal interval is no stranger than a law that refers to both ends of a spatial interval. The asymmetry we perceive, causation running from past to future, not future to past, is a feature of how we, as IGUS, interact with the block, not a feature of the block itself. The physicist John Wheeler, who coined the term black hole and mentored Richard Feynman, proposed a thought experiment in the 1970s called the delayed choice experiment. The experiment is a variant of the double-slit experiment, but with a twist. The choice of whether to measure which path a photon takes is made after the photon has already passed through the slits. In the standard double-slit experiment, a photon passes through two slits and generates an interference pattern on a screen, as if the photon went through both slits simultaneously. But if you measure which slit the photon goes through, the interference pattern disappears, and the photon behaves as if it went through only one slit. Wheeler's delayed choice setup uses a mach-zehnder interferometer, a device with 2 beam splitters and 2 mirrors. A photon enters the interferometer and encounters the first beam splitter, which sends the photon down 2 possible paths. The paths recombine at a second beam splitter, and depending on the phase difference between the paths, the photon exits through one detector or the other with predictable interference. The delayed choice is whether to insert the second beam splitter or remove it. If the second beam splitter is in place, the photon interferes with itself, and you see quantum behavior. If the second beam splitter is removed, the photon goes down one path or the other, and you see classical particle behavior. The choice is made after the photon has already passed the first beam splitter, long after it has decided whether to behave as a wave or a particle. Wheeler predicted that the photon's past behavior depends on the future measurement. If you insert the second beam splitter, the photon behaves as if it took both paths. If you remove it, the photon behaves as if it took one path. The future choice affects the past path. The experiment has been performed many times, and Wheeler's prediction is confirmed. The delayed choice does affect the outcome in exactly the way quantum mechanics predicts. The photon's path is not determined until the measurement is made, even if the measurement is made after the photon has already passed the point where the path would have been chosen. One interpretation is that the photon does not have a definite path until the measurement. The path is not a pre-existing fact, it is generated by the measurement, retroactively assigning a history to the photon. Another interpretation is that the photon's state is a superposition of both paths, and the measurement collapses the superposition, choosing one path over the other. A third interpretation is the two-state vector view. The photon's state is determined by both the initial preparation and the final measurement, and the path is a classical concept that does not apply to the quantum state. All 3 interpretations agree on the predictions. They differ on what the mathematics means, and none of them supports the intuitive picture of motion as a definite real-time trajectory through space. The delayed choice experiment was performed over a very long baseline in 2007 by a team in France. The photon traveled a distance of 48 meters before the delayed choice was made. 48 meters. The photon's past was not determined until the experimenters decided, 160 nanoseconds later, whether to measure which path it took. If the photon's path is not real until the measurement, then the past is not fixed until the future measures it. This is not time travel, it is something stranger. It is the possibility that the past, as a collection of definite facts, does not fully exist until the future has constrained it. The block universe in this view is not a static, eternally fixed structure. It is a self-consistent solution to a set of constraints that span the entire block, and the constraints include future measurements as well as past preparations. But even this retrocausal reading does not restore genuine motion. It replaces a forward-flowing dynamics with an all-at-once constraint. The world line of the photon is still a static object in spacetime, and the appearance of motion along the world line is still the internal perspective of a structure that from the outside does not move. What does it mean to say the outside does not move? Is there an outside? David Lewis, in his problem of temporary intrinsics, illustrated the issue with the example of being bent and being straight. The solution was to say that you are bent at one time and straight at another, and the at is implemented by distributing the properties across temporal parts. But there is another way to read the problem. You are bent while sitting. You are straight while standing. The properties bent and straight are relational. They describe how your body parts are arranged relative to each other. And the arrangement changes. The change is real. You go from being bent to being straight, and that is a genuine transformation, not merely a static distribution of properties across parts. The endurantist holds on to this intuition. Objects do change. They do not merely have different properties at different times, they genuinely alter, and the alteration is an ontologically primitive fact. The bent U and the straight U are the same object, wholly present at both times, and the transition from bent to straight is a real process, not a redescription of a static geometry. Trenton Merricks, an endurantist philosopher, has argued that perdurantism eliminates genuine change. If change is just the possession of different properties by different temporal parts, then nothing is actually changing. The parts are static, they always had the properties they have. There is no object that undergoes a transformation. There is only a series of distinct objects, each frozen in its own configuration, and the change is a matter of how you describe the relationship between the parts. The endurantist calls this a crazy metaphysic, a view that abolishes the very phenomenon it was meant to explain. Change, Merricks insists, is not a distribution of static properties, it is something an enduring object does. E.J. Lowe, another endurantist, argued that objects are wholly present at each moment and that their properties are had relative to times, without the object being divided into temporal parts. When you are bent, the whole of you is bent at that time. When you are straight, the whole of you is straight at that later time. There is no thin slice that is bent and a different thin slice that is straight. There is one object enduring through time, first bent and then straight. The relativization to times handles the apparent contradiction without slicing you into parts. The disagreement between the perduranist and the endurantist is not settled by any experiment. Both views are compatible with all the physics. They differ on the metaphysics, on whether objects are extended through time as they are through space, or whether they are wholly present at each moment. And this is where the honest limit of the science must be drawn. Consider two surveyors hired to map the same stretch of coastline. One works from the sea, measuring the water's edge. The other works from the land, measuring the cliff's base. They produce different maps, and they argue about which is the real coastline. But the coastline is a single geometric fact, and the disagreement is about which features to emphasize, not about the underlying terrain. The dispute between eternalism and presentism may be like this: a disagreement about how to describe a shared geometry, not a disagreement about the geometry itself. Several philosophers, Stephen Savitt, Mauro Dorato, John Norton, have argued exactly this, that the debate between the two positions may be, in the end, a verbal dispute, with both sides describing the same physics in different vocabularies. Or it may be a genuine disagreement about what exists, one that no measurement can resolve because both positions predict the same observations. This is the deepest problem. Eternalism and presentism, worm theory and endurantism, are empirically underdetermined. They agree on every experiment. They agree on the clock readings, the interference patterns, the gyroscope drifts. They disagree only on what lies beneath the observations, and that disagreement is not accessible to measurement. Here is what the evidence shows, and here is what it does not. The physics is not in doubt. Special and general relativity are among the most precisely tested theories in the history of science. The hafele-keating experiment confirmed that time is frame-dependent, disagreeing by nanoseconds over a 3-day flight. Gravity probe B confirmed the geodetic and frame dragging effects to within 0.1% and 5% respectively. GPS satellites correct for relativistic time dilation every second of every day, and the corrections work. The relativity of simultaneity is real. There is no observer-independent now. The spacetime interval is invariant, and the four-dimensional geometry Minkowski described is the correct mathematical framework for physics. From this, one conclusion follows robustly, and it is not seriously contested. The four-dimensional geometric description, in which motion is encoded as the static structure of a world line, is the correct description of the physics. When your hand slides across the table, the physics describes a world tube, a static, four-dimensional shape whose cross-sections are the hand's configurations at successive times. Velocity is the slope of that shape. Acceleration is its curvature. There is no additional dynamical ingredient, no moving through over and above the geometry. The at-at theory of motion is the correct physical account. An object is at different places at different times, and that is all there is to say, physically, about motion. This part is settled. What is not settled is what the geometry means. Is the four-dimensional block ontologically complete? Is that all there is, with the flow of time and the moving present being nothing but features of consciousness embedded in the structure? That is eternalism, and it is, as Dean Buonamano notes, the favoured view in physics. To the extent that there is a favoured theory in physics and philosophy, it is certainly eternalism. Or does an objective present also exist, a genuine passage that the geometry fails to capture, as the presentists Ned Markosian and Dean Zimmerman, and the endurantists E.J. Lowe and Trenton Merricks maintain? Eternalism fits the physics with elegant economy. It requires no preferred foliation, no objective present, no extra structure beyond the space-time geometry itself. It resolves the problem of temporary intrinsics cleanly, through temporal parts. Its strain is phenomenological. It must dismiss the flowing present, the felt passage of time, as an illusion. And while the neuroscience of post-diction, the Libet delay, and the free-fall 36% memory distortion show that felt time is heavily constructed. Showing that felt time is constructed is not the same as showing that no passage exists in reality. Absence of evidence for objective passage is not proof of its absence. Presentism fits experience. It takes the moving present at face value. Its strain is the physics. To maintain an objective global now, it must posit a preferred foliation of spacetime, a privileged slicing that relativity does not provide and that no experiment has ever detected. It must treat the relativity of simultaneity as a mere appearance concealing a hidden absolute frame. This is a heavy cost, and most physicists judge it too heavy. But here the argument that seemed to settle the matter falters. The Wright-Dike-Putnam argument claimed that relativity forces eternalism. Howard Stein showed that it does not, that a coherent notion of an open future, defined through the light cone structure, survives in special relativity. The inference from no universal now to the future is already fully real and determined is not deductively valid. And Savitt, Dorato, and Norton have argued that the whole dispute may be less substantive than it appears, that eternalism and presentism, when carefully stated, may agree on all the physics and differ only in vocabulary. So this is what the evidence supports. The four-dimensional geometric description of motion is correct. Motion is the shape of a world line, and there is no dynamical moving through in the physics. The intuitive picture of a single object crossing space in a flowing present is not the picture the physics gives. To that extent, the title's claim holds. Understand the shape, and motion, as you intuitively conceive it, stops being the fundamental fact. It becomes geometry. What the evidence does not settle is whether that geometry is all there is, whether the block is ontologically complete, or whether an objective passage of time also exists, is empirically underdetermined. The two readings agree on every measurement. No clock, no gyroscope, no interferometer can distinguish them. And beneath even that lies the deepest question of all: whether the flow of time, and therefore genuine motion, is a feature of the universe itself or only of conscious experience within it. Here the science reaches its limit, and it is honest to say so. The physics describes the geometry with extraordinary precision. It does not tell us what the geometry ultimately is, or why there is a structure to be experienced at all from the inside. That question lies beyond what any measurement can settle, and it remains open. Let me bring this to a close. We began with a hand resting on a table, and the ordinary certainty that when it slides, it moves. We traced that certainty through Minkowski's spacetime, formalized in Cologne in 1908, where space and time fused into a single four-dimensional structure. We followed the world line and the world tube, the temporal parts that compose them, and David Lewis's perdurantism, which reconceived every persisting object, including you, as a shape extended through time. We watched the at theory of motion dissolve the moving through into pure geometry. We saw the relativity of simultaneity confirmed by hafele-keating's atomic clocks, by every GPS satellite, by gravity probe B's niobium spheres drifting by milliarc-seconds in orbit. We stood at the edge of a kerr-ergosphere, where standing still is geometrically impossible, and inside Gödel's rotating universe, where worldlines close into loops. We watched the free-fall subjects estimate their own terror as 36% longer than it was, and learned that the present you feel lags reality by up to half a second, stitched together postdictively by a brain that, as Craig Callender put it, treats manifest time as more or less rubbish. And we arrived here. The evidence robustly supports a four-dimensional geometric description in which motion is the static shape of a worldline, not the act of a traveler crossing space. That much the clocks, the satellites, and the gyroscopes have shown. What they have not shown, what no measurement has shown, is whether that geometry exhausts reality, or whether an objective passage of time also exists, felt as flow, real as experience, silent as physics. The interpretations agree on every observation and diverge only beneath them, where instruments cannot reach. Whether the flow of time is a feature of the cosmos or only of the mind embedded within it, is a question the physics cannot presently settle. That is not a failure of the science, it is an honest map of its edge. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. The hand never crossed the table. The shape of the crossing was always there, a diagonal ribbon in a geometry that does not move, being read, one cross-section at a time, by whatever it is that noticing feels like.